All right, sir, we are live.
Hello
Mic check
and
in the
welcome
chat,
to Aether
please.
Cosmology Roundtable number 29. Today I'm going to be presenting on geomagnetism.
All right, sir, we are live.
Oh,
Mic check
sounds
in
like
the
I have
chat,
a
please.
Ether
Tab open.
Cosmology
Whoopsies.
Roundtable number 29. Today I'm going to be presenting on geomagnetism.
All right, sir, we are live.
All right, there we go, fixed. Sorry. All right. So I'm going to be presenting on geomagnetism. Let's go ahead and get into it. We're going to talk about measuring the geomagnetism on the Earth. We're going to talk about prerequisites for geodynamo theories. We're going to talk about astronomy, geology, seismology, and then we're going to get into geodynamo theories. We'll talk about a physical dynamo that was built. We'll talk about dynamic theories of the geodynamo, and we'll talk about kinematic theories of the geodynamo. And then we'll talk a little bit about alternative theories as to what is going on with the magnetism on the Earth. So, measuring geomagnetism. In a simple term, people will tell you that Earth is like a bar magnet. You'll find people such as Professor Dave, quote unquote, saying this, and Neil deGrasse Tyson will say this. But if the Earth functioned like a bar magnet, its poles would have attracted ferromagnetic particles from the atmosphere over, in their model, 5 billion years, resulting in the formation of huge ferromagnetic mountains at the poles. And you'd have a hypothetical magnet with the Earth's mass, which would be approximately 6 times 10 to the, or 6 times 10 to the, it looks like I have a broken figure there, or so 6 times 10 kilograms, extending its magnetic field. It would extend its magnetic field 40,000 miles into space, create a massive mountain. It'd be a very intense field at the point of the pole. But what we actually have looks like this. This is a proposed picture of the North Pole. You can see at this point in this picture, there is not even any ice underneath the pole, let alone a magnetic mountain. So the Earth, the reason we don't have that, or at least likely why we don't have that, is because the Earth is electromagnetic, not ferromagnetic. A compass needle orients itself perpendicular to an electromagnetic field. And what you see here is you see a conductor of electricity going here, and it causes electromagnetism via the right-hand rule going around these points here. And so a compass actually orients itself along this point, or along these lines here. And so when your compass is pointing to the North Pole, it's aligning as so to match these lines of electromagnetism. Magnetic north is something we're all familiar with, and it's the idea that a compass aligns parallel to, well, so in my terms, I would say the compass aligns parallel to dielectric force and perpendicular to the magnetic field. Not as simple as just there's like a pulling force. There's no such thing as a pulling force in the first place, but nothing pulls your compass needle towards the North Pole. It's being aligned perpendicular to a magnetic field along parallel to lines of dielectric force. And the geomagnetic North Pole, so you've got a few different things here. You've got magnetic north, but that brings into scope the idea of the geomagnetic North Pole, and that's the model-based area where the geomagnetic field is perpendicular to the surface, and Aurora Borealis tends to surround the geomagnetic North Pole. There's also the magnetic North Pole, and that's the point towards which a compass orients, and where the magnetic field should be oriented vertically downwards, and that wanders over time. And then there's also the geographical or celestial North Pole, and that's the location at which the North Celestial Sky's rotational axis is at the zenith. And these are all different places on the Earth. And here we show a map of the moving North Pole according to them and their data. I would say by them, we'll get into that in a little bit of where magnetic data comes from. But this is what's proposed to have been happening over the last 200 years or so, in that the North Pole has moved from Canada to the center, more towards the center of the quote-unquote geographical North Pole, and is heading, in their estimation, towards Russia. Now, a quick note here. We haven't gotten into the geodynamo theory yet, but in the geodynamo theory, the reason that these poles are in different places is because the convection currents in the outer core are not aligned with the Earth's proposed axis, despite Coriolis being invoked as the central cause of the columnar helical orientation of the currents. Like I said, we'll get into that in a bit. The important thing here is just to take a quick look at this diagram and notice that the magnetic field does not align with what they call the rotational axis. So how do we measure the magnetic field? Well, there are tools we can use called magnetometers. And here's a flux gate magnetometer. And this uses a magnetic core and coils to detect changes in magnetic saturation caused by external fields. There's a such thing, it's called a proton precession magnetometer. This detects magnetic fields by measuring the frequency at which hydrogen protons realign and precess after the removal of a strong external magnetic pulse. And then there's optically pumped magnetometers. And these are scalar magnetometers that use excited atoms like cesium or rubidium affected by magnetic fields and changes in atomic energy states. And they take optical measurements of that to get a reading of magnetic intensity, essentially. Then there's a squid magnetometer. I didn't get a chance to look into these much, but the idea is that extremely sensitive devices measure minute magnetic fields using superconducting loops and quantum interference. Will be maybe a thread to look down later. And so then going back in time to when they first started measuring the magnetic field, they started with using something called Fox's dipping needle. And here's a diagram of that, and here's a picture of such. The important thing being that it shows not just magnetic directionality, but also the dip of the magnetic field, because the magnetic field's the strength of the magnetic field is not directly horizontal to the plane. It actually goes points up and down as you move to and fro the pole, or towards and away from the pole. So there's a picture of it again, and these were used back in the 1800s. Extensive magnetic surveys were commissioned, aimed to improve maritime navigation, and geomagnetic science, quote unquote, was conducted, led by figures from the Royal Society such as Sir James Clark Ross and Edward Sabine. And the Earth's magnetic field was mapped. They looked for anomalies. They wanted to get better compass accuracy, quote unquote. And here's a quote taken from Erebus by Michael Palin. It says, "They had crossed the magnetic equator on the 7th of December when Ross had noted a satisfaction that the needle on his Fox dip circle, a device used to measure the angle between the horizon and the Earth's magnetic field, was perfectly horizontal. He had seen it point directly upwards at the North Magnetic Pole, and assuming the expedition was successful, would witness it point south, or point straight down when they reached the South Magnetic Pole." So that's straight from Mr. Royal Society, Sir James Clark Ross, or via Mr. Michael Palin. Thank you, Mr. Michael Palin. There he is, Mr. James Clark Ross, with his little Fox dip needle. Ooh. And here's a picture of his expedition down in the south. And then here's showing, kind of hard to see, but there's where Shackleton is said to have gone as far in as. And then if you look here, this is as far as Mr. James Clark Ross was said to have gone. So, pretty cool guy. Pretty brave explorer, they would say, huh? Now, getting into more modern measurements of the magnetic field, in 1979 they launched MagSat, and that was equipped with vector magnetometers, or magnetometers, and scalar magnetometers, which are the same thing as those optically pumped ones we were talking about, and it was using helium, and it operated in low Earth orbit from October 1979 to June 1980, collecting magnetic data, on a new scale. And then in 1999, Ørsted was launched, and that was equipped with fluxgate magnetometers and a scalar magnetometer, and that provided more detailed measurements of the Earth's magnetic field to help understand its dynamics and secular variation. until that's supposed to say until 2014 when it was taken out of commission. And actually, I believe it was sooner than that. So that's a typo. So then in 2013, Swarm was set up, and this was 3 satellites that were launched that are still in operation, and they use vector field magnetometers, which is a combination of various fluxgate magnetometers on multiple axes and scalar or optically pumped magnetometers to map the magnetic field in high resolution. These operate in quote-unquote near polar orbits, continuously collecting data to track changes in the magnetic field over time. And if you think about near polar orbits, that allows it to go basically back and forth as it would now if you were on a, let's say, an azimuthal equidistant projection map, it would do like a flower of life pattern that with very thin, long petals, right? So that's what these would do, and that allows it to cover a large portion of the Earth. The Earth's magnetic field is asymmetric, and its changes over time are anomalous. This is not as simple as a bar magnet by any means. And what we have is magnetic declination. And it is claimed that a compass aligns with the Earth's magnetic field pointing towards magnetic north, not directly to the north magnetic pole. And so what that means is that you follow a compass. If you were to follow a compass, you would eventually get to the north magnetic pole, theoretically, they say. But it would not get you there via the shortest path. It would take you on curves and twists and turns, maybe even like, down away from where you're going. And that's due to the asymmetry and the anomalies. And because of that, they per this this framework that was given to us after the Royal Society expeditions, we have navigation corrections for magnetic declination in the south, and those can vary dramatically. In some regions, the magnetic declination can reach extreme values, requiring navigation corrections up to 92 degrees. And here's a picture showing the incongruent or the asymmetric field declination of the north versus the south. As you can see, they're totally different looking. You have something that looks almost like a quadrupole here, and then in the south here you have just like, looks like 2 poles that are next to each other. Very odd looking. And there's a larger picture of that in the south. That's the main field declination in the south, and here's the main field declination in the north. And so then these projections are used to make corrections within navigation. Now, just looking at the data that we have from what they say comes from these satellites. When I say they, I say NASA and the space agencies that hand us down this data. We have so we have this to look at, right? And we have the main field inclination. This is it pointing essentially perpendicular or not? And then we have the horizontal intensity. So this is how strong is the intensity of the magnetic field on the horizontal axis. And then we have the main downfield component. So this is how strong is it pulling downwards, essentially. And then we have, so yeah, interesting maps. Kind of gives you an interesting idea of what's going on with our magnetic field. Now, secular variation refers to the slow and gradual changes in the Earth's magnetic field over time caused by complex motion of molten metals within the Earth's outer core, which again, we will get into in a little bit. These changes alter the strength and direction of the magnetic field at various locations on the Earth's surface. And secular variation was first recognized in 1634, as it's said, by Gellibrand. And he was comparing magnetic declination observations he made in London with earlier observations. And the observations of declination over the years are still used today to show one of the best, records of secular variation over time, but they only go back as far as the 1630s, supposedly. I believe they started getting a bit more serious about it around here. Interesting, when it started going up. So let's talk about more evidences and more effects of the magnetic field on the Earth. Aurora Borealis and Aurora Australis are said to be caused by solar winds interacting with the Earth's magnetic field. Aurora Borealis in the north is more frequently observed and typically more colorful with more emerald greens, whereas Aurora Australis in the south is a bit less frequently observed and is more commonly pink. Here's a picture of Aurora Borealis. Nice, beautiful emerald green. Here's a picture of Aurora Australis, a beautiful pink in the sky. Solar wind deflection. It's claimed that the Earth's magnetic field keeps us safe and plays a critical role in deflecting the solar wind. And without that, the atmosphere would be stripped off into space. That assertion is reified via observations of celestial bodies and their interaction with solar wind. This assertion is reified via observations of celestial bodies and their interactions with solar wind. So they look in the sky and they say, hey, look at that thing in the sky is having this effect that we calculate to be, or that we estimate be happening on Earth, and thus it must be happening on Earth because the Earth must be a globe. So rock magnetism they also use to verify, or that they say to corroborate this. And that's some rocks preserve Earth's past magnetic fields, which geologists study to understand changes over time. So now, before we can talk about the geodynamo, we've already kind of started setting things up, but we need to get into some of the prerequisites for a geodynamo theory. So first, we have to start with astronomy. And if you go pick up an Introduction to Seismology textbook, then what you're going to find is that the first unit or the first chapter or few chapters are all going to be about astronomy, because you have to presuppose that the Earth is a sphere before you can start doing meaningful seismology according to them. And so in order to get us on the right path here, get us in the right mindset for doing seismology, we're going to look at this picture from space. This is, I believe, a real picture from NASA. And so just take this in, make of this what you will. You see balls in space, you see some curvature on the horizon. So we're going to just understand here as we move forward that the ground beneath our feet is a spinning ball. And we're going to take into account the kinematic solar system. So if you can bring yourself to the level of a mindset of these children with these styrofoam balls, then we're going to be on track to understand the geodynamo. And so just understand, just go ahead and just look here and understand that the square of the orbital period is directly proportional. And so really, we can just take Kepler's kinematic laws and apply them directly to Newton's laws, because it turns out that Newton's laws are just kinematic anyways. So, we're just talking about kinematics in the sky. This is pretty easy to take in. And this could be you. If, now that we've looked at the pictures of space and we've understood the solar system and how cool the solar system is, we now know that this could be us. We could be an astronomer. Now let's talk about seismology. So the layers of the Earth, we have the crust, we have the mantle, we have the outer core, and we have the inner core. And it's said that the crust is about 700 kilometers thick. You've got, I think we're getting into we're getting into the mantle right here. So actually we go 0 to 100 kilometers thick is what they're saying on this chart for the crust. You've got the idea now. They've been talking about the asthenosphere, which is kind of like the middle ground area between the two. Here's another one, continental crust and the oceanic crust on the top, about 5 kilometers thick. And then as you start going, did I hear something?
100 kilometers thick.
Yes. But I guess we're getting into the lithosphere with that.
Yeah, I think they were echoing you.
Oh, gotcha. Okay. So you got the uppermost mantle, and then partially molten asthenosphere, the solid asthenosphere, mantle transition. Here is showing the temperatures. This is crucial to understand here. So in the crust, we are way down here between 0 to 100. Way down here, right? This is a sliver. And we are barely showing in the thousands of degrees chart on this axis. And as we go down into the upper mantle, lower mantle, outer core, inner core, you see the temperature goes up pretty drastically at certain layers, especially between the lower mantle and the outer core. drastically hotter in the outer core. We're going from 2000, 2200 or so up to 4200 or so. And notably, while we're here looking at this, so 5,000 degrees would be about here, right? 5,500 would be about, yeah, right around here or so. And the surface of the sun is theorized to be 5,500 degrees Celsius. So the core of the Earth is hotter than the surface of the sun as per mainstream physics. Now, moving on from there, really quick, let's discuss Newton's shell theorem. So the Earth's dense iron core is located at the point of zero gravity. We just looked here. We have this inner core that is solid despite these intense temperatures, and it is said that it is located at the point of zero gravity. So the iron core is not necessary to invoke point-specific gravity, which we'll talk about in just a second. That's actually a typo there, or that was a revision of it. Let's revise that fact right here, right now. I misspoke about this previously, and that's required. But the shell theorem does allow for the uniform downward bias across the Earth. The thing is, so on the outside of a shell, let's say we're trying to have a planet, quote unquote, materialize from things in the vacuum of space. Well, if we had a shell, and I'm standing on the outside of said shell, symmetric force vectors on that shell are going to pull me down equally in all directions. Now, this is assuming, of course, that the shell is perfectly uniform in its mass, but I can stand outside of that shell, and because of the symmetric force vectors pulling me down, it's theorized that I would have a uniform downward pull. Now, the problem is, on the inside of the shell, you're going to have asymmetric force vectors. So you could not stand inside of the shell anywhere, because as you move here, you're going to be pulled in different directions in all different ways. So notably here, in order for a planet to materialize, you have the point of zero force being where, in their theory, they end up having, hot iron cores, or, they have, there's a problem literally a problem at the core of all of these theories in the heliocentric model, in that, like, you're believing in something as real as the idea of a perfect circle in order to believe in this to exist. You're taking on like a whole paradigm of Newtonian gravity that is paradoxical, or at least unproven. Now, seismology teaches us, according to their theory, that there are P and S wave shadow zones. So you have, what that shows is that around the central point of a quake. Now, on an azimuthal equidistant map, this would just essentially be an area around the point of the quake. You will get the S waves, but the P waves are said to be felt across the Earth, and this is what they say the P waves do. They say that they shoot through the core, and because of the liquid outer core, something about the way that the liquid outer core, what's the word I want, propagates these waves, there's actually like a refraction that occurs, and so you get these shadow zones, P-wave shadow zones, and they're said to be proof of much of what we're going to get into in regards of the inner and outer core. Now, observations, really quick, let's just put it out there that observations frequently do not match their predictions. Localized responses frequently occur hundreds of miles from the expected origin points before the asserted origin point even has had a quake. And the observations of the crust have not matched predictions. So when they're doing their calculations and they're taking their velocities into account, they're taking into account the mineral makeup of the crust in order to do their calculations of any of these things. Well, it turns out that every time we actually go and dig into the crust, the direct observations of the crust don't match their predictions. So this is essentially meaningless. Now let's talk more about geology, because magnetogeology is another crucial part of how we get into them explaining what the magnetic field does. And really quick, I'm going to take a drink of water. All right. So there's oceanic magnetic striping at the sea ridge. The foundation of all geological theories comes from paleomagnetic signals, which are found locked in rock at the spreading seafloors at the oceanic ridges, and it's claimed that these trace back hundreds of millions of years in the past. Let's take a look at what that looks like. So you have magma coming up and at the sea ridge, and as it cools, it's said that it cools with the polarity of the ferromagnetic magma to be aligned with the current magnetic field. But if you go outwards from the ridge, you'll find an area of reversed magnetic polarity. Now, in their model, this magma keeps oozing out, and these plates keep sliding outwards in both directions. And you'll see a stripe, you'll see a mirroring of this effect on both sides. Here's another picture kind of showing what's going on with that. So you have the more magnetization. So this is like a different way that they would, this is a different approach to looking at the geology of it. But basically they're looking at the amount of magnetization here at a sea ridge. But then here's another image showing, this kind of shows the time spread, right? So they're saying that we have present day magma coming out at a specific rate that they assert must have always been the same over millions of years, and that as that happens, as the polarity, the magnetic polarity of the Earth switches, the orientation of the ferromagnetic properties of this cooling magma is going to switch. So they see it switch back and forth in stripes on both sides across the ocean floor, and they assert that that means that over this many years of time, it has the magnetic field has flip-flopped. And that is the main primary evidence that they cite for the flip-flops of the magnetic field, or of the magnetic field. And they were proposed by Harry Hess in 1962 in the History of Ocean Basins. They are anomalous and inconsistent, and we're currently running behind by about 520,000 years, which is about 2 times the expected period. So it's been, 300, we're at like a 300% now at this point, essentially. Here's showing what's going on with it. The field polarity reverses, at around every 250,000 years, but it's been 780,000 years since the last reversal. Just kind of showing, them looking at striping and deducing this. Now, before we accepted this with faith as, their theory with faith as the for sure explanation of everything, here are some other previous field reversal theories. One was that intrusions of magnetic material caused distinct material. Caused by large intrusions of magnetically distinct material into the oceanic crust. It assumes that the intrusions had different magnetic properties than the surrounding rock, and that created magnetic striping patterns. Another possibility is that localized geological activity caused... Sorry, I wrote this kind of weird. Localized surfaces for magnetic variation, such as volcanic activity or the regular deposition of highly magnetic minerals, created striping patterns. Another possibility is that the poles moved across the Earth's surface, and the magnetic minerals in the oceanic crust recorded the varying positions of the poles. And then another possibility is that vertical movements of the Earth's crust caused differences in magnetism, and that was caused by changes in the elevation of the ocean floor, which affected the Earth's magnetic field locally. So you could have the fact that literally the crust moved up and down, the poles wandered, localized geological activity caused magnetic variations, or intrusions of magnetic material could have affected that. Now also, the timescales are a massive leap of faith. There's no reason that we should assume that this amount of time that this magma has been coming out, the amount of time and the rate at which the magma has been excreted or coming out at the ocean ridges has remained the same over millions of years, especially when our sampling size is, minuscule. During reversal, if the field were absent, that would cause a hypomagnetic effect, of which much research has been done. So I think there's even a I believe there's even like a Hollywood film about being afraid of the reversal of the magnetic field. Now, what it means by hypomagnetic is that that's the absence of any magnetic field. And it turns out that that's not very good for a person. And there's a ton of studies on this. So shout out to @SuspiciousObservers on YouTube for pointing out all these studies. So I'm just going to read some titles here. Using a 120 centimeter cyclotron to study the synchronous effects of ionizing radiation and the hypomagnetic conditions of the simplest biological effects. The effects of different durations of exposure of hypomagnetic field on the number of active mitochondria on ROS levels in the mouse hippocampus. Here, this study found hypomagnetic field during embryogenesis led to an increased mortality of embryos. Reactive oxygen species, potential regulatory molecules in response to hypomagnetic field exposure, biological effects of hypomagnetic field, ground-based data for space exploration, decline of cell viability and mitochondrial activity in mouse skeletal muscle cell in a hypomagnetic field, hypomagnetic fields and their multi-level effects on living organisms. A hypomagnetic field aggravates bone loss induced by hind limb unloading in rat femurs. The peculiar features of cognitive processes in rats exposed to a hypomagnetic field using moderate magnetic shielding. Radical triads, not pairs, may explain effects of hypomagnetic fields on neurogenesis, an influence on hypomagnetic field on the heartbeat in zebrafish embryos, effects of hypomagnetic conditions and reverse geomagnetic field on calcium-dependent proteases of invertebrates and fish. Long-term exposure to a hypomagnetic field attenuates adult hippocampal neurogenesis and cognition. That's a fun one, or it sounds like a fun one. Hypomagnetic field causes anxiety in adult male mice. And so, yeah. Now, just one quick thought. When I read through all this, now all I did is look at these titles. But when I saw these titles, one of my first thoughts, and something I'm going to want to look into more, is if people are going to quote-unquote outer space, I'm thinking the hypomagnetism might be one of the biggest problems to consider. Or the hypomagnetic effect, rather. Now, moving on, there are, as they say, there are other archaeomagnetic artifacts. These are objects containing magnetic minerals that were heated to a high temperature in the past and then cooled down in the Earth's magnetic field. Because once you heat to a certain point, you go past the Curie point, you lose your magnetic orientation, and then as you're cooling back down in the Earth's magnetic field, you show your orientation. That's what happens with ferromagnetic minerals. So, the magnetic orientation of lava flows is used to make claims about the Earth's past magnetic field direction and intensity at historical times of the solidification of lava. So by analyzing those orientations across multiple lava flows of what they say are different ages, scientists claim to reconstruct changes in the magnetic field. And also they say that lake sediments can be used, and they say that as things accumulate at the bottom of lakes, that they contain magnetic minerals that align with the Earth's magnetic field at the time of deposition, and by analyzing the magnetic properties of layered sediment cores extracted from the bottom of lakes, scientists claim to trace variations in the magnetic field back throughout time. Now, in their model, I think many of us are familiar with plate tectonics to a point, but let's just go over it real quick. The foundation of geological theory and plate tectonics originates and conforms to magnetogeology. Now, those ocean ridges we were talking about, where the magnetic striping originates, is, I believe, going to be over here. But it's all, it's all kind of a web together, right? It's all within the same. Conceptually, this is all the same globe. This is, we've got plate tectonics. We've got magnetogeology showing the ocean striping and the field reversals. And we've got a bunch of claims about the crust. We've got a bunch of claims about the inner and outer core. And the mantle must necessarily conform to certain parameters to exist between those two areas and to not allow the heat from the 6,000 degree inner core to conduct out to the surface. So a rotating globe, really quick, what should a maximum momentum, minimum energy state look like? If we have a semi-liquid interior, That should accentuate the lack of uniformity in our rotation. And more importantly, with plate tectonics, the continents should actually drift outward to align the equator. That's what a true centrifugal force should necessitate. But what we actually have is this idea of Pangea, where not the continents never aligned the equator, the mass never aligned the centrifugal location where it should end up at, but instead we had a big lump, and that would cause. But if you think about it, that would cause great instability. So it's it's an interesting theory, and pairing that with the semi-liquid interior, uniform rotation is essentially impossible, and that's all foundational to geophysical assertions of the globe. And they also they have their idea of stratigraphy, and this is studying rock layers, strata, and their arrangement in order to understand Earth's history and the relative ages of geological formation. So there's lithostratigraphy. We're going to just, so all these things they use to reify each other, essentially. It's an interesting game you can play of chicken and egg, but with 4 chickens and eggs, basically. So lithostratigraphy is correlation of rock layers based on their lithology, composition, and physical characteristics. Magnetostratigraphy uses magnetic polarities preserved in rock layers to establish chronological sequences. And then biostratigraphy utilizes fossil content within rock layers to determine the relative ages of geological formations. And then conveniently, chronostratigraphy correlates rock layers based on their absolute ages, typically using radiometric dating methods to establish a chronological framework. We all know radiometric dating is so insanely accurate, obviously, and we've corroborated that too, because we can go back millions of years and hundreds of thousands of years and corroborate it. Obviously, we can't do that, being facetious. The great unconformity. So we have these precepts. We have the idea of stratigraphy. There are actually specific laws that state that essentially as you go further down, you're supposed to have, there are very specific rules that state as you go down, you go essentially back in time according to their model. In the geological record, you go further back in time. But the great unconformity is a significant anomaly in modern geological theory wherein older Precambrian rocks are directly overlain by much younger sedimentary rocks, always with a substantial gap in the geological record. And that gap can represent hundreds of millions to over 1 billion years of missing rock layers. And that highlights a period of intense erosion and or non-deposition that occurred before the deposition of the younger layers. Okay, interesting. So here's showing what that looks like. This is specifically to the Grand Canyon. You have these layered Paleozoic rocks, and then you see this way older time period merging straight into it. So what happened in between and how it... Now, could it be that their time scales are just all wrong and that this was maybe just one event that occurred? I would say yes, but no one can really corroborate one way or the other because no one can go back in time millions of years. Here's a picture of the Great Unconformity. We have, around 495 million years ago with the Sawatch Formation, and then going back just 1,030 million years ago with the Pikes Peak granite. So, or going back all the way back. So this is 500 million years, just boom, poof, missing. Must be 500 million years though. Here's another picture. This one is also from the Rocky Mountains. Just showing, two totally different geological timelines. 500 million years missing in the middle. So, thinking of all this, now we get into the idea of the crust-mantle boundary. And that's another area that's never been observed or meaningfully measured. It's just calculated and deduced from theory. So let's try and see what we can deduce as we go down in the crust. Maybe we can learn something about the crust-mantle boundary, or maybe we can learn just something about the crust. So in the 1970s, Soviet scientists wanted to learn. So they hoped to drill down 1,500 meters in order to study the Earth's crust. It is now the Kola Super Deep Borehole. So this was called the Kola Super Deep Borehole. And it is now bolted down and welded shut. There's a picture of it. You wanted to, go take a journey 1,500 kilometers down, or sorry, 1,500 kilometers down, you could hop in there. So it's the deepest hole on Earth. It's deeper than the Mariana Trench even, and they drilled it for 24 years. It was expected that they were going to reach 15,000 meters, or sorry, 15,000 meters, and they reached only 12,000 meters. And just for, scale, just to kind of put it in perspective, that's 0.002% of the way to the center of the Earth. And they used pressurized drilling mud and a custom drill bit, and a bunch of novel instrumentation was invented specifically to take measurements. And water was found at depths not expected. They say it was squeezed out of the rock crystals. It has never been observed elsewhere. It does not comport with their theory. And fossils were found at depths up to 6.7 kilometers, which is also not comport with their theory. And past the 12-kilometer mark, heat and pressure became a massive technical issue. And that's why they didn't make it past much farther past 12 kilometers. They expected the temperature at 12 kilometers to be around 100 degrees Celsius, and it was actually 180 degrees Celsius. And the rocks, they said, were behaving like plastic. Now, the Earth's mantle doesn't even begin until 35 kilometers. So we only made it to 12 kilometers, and we were 80% off on the temperature that we expected. And also, they did not expect the rocks to be behaving like plastic quite yet. So then also in 1983 in Oklahoma in the United States, there was an oil exploration well that inadvertently became one of the deepest holes ever drilled. And yet again, much higher temperature and pressure was found than they expected. And they reached a depth of about 9,500 meters before they abandoned the whole thing due to encountering molten sulfur. And molten sulfur was not expected to be encountered, but thanks to the temperature and the pressure both being much higher than expected, they ran into it. So they were off yet again in their predictions about the crust. But, we still see things about the coral mantle boundary. We're going to assert that it exists and that it must be as we think it is. As pressure increases, the temperature necessary to melt minerals gets higher. So you see what happens here. Don't get confused. I got confused when I first looked at this. You have two different charts with axes on both sides. But what's happening here is you see that as you go down and the temperature goes up, the pressure is also going up because of the depth. And you have this dance of the melting point because of the change in the temperature and the pressure. And then here you have the velocity and density. I believe this is of motions in the mantle, but I can't see. But that comes from Carnegie Earth and Planets Laboratory. Shout out. So modern theories maintain the idea that if the inner core of the Earth were even just around 100 degrees Celsius hotter, it would be liquid. So really want to pause here and drill that home. And they only say this because really they don't know how it works. And the crystal lattice orientation of the inner core is like a massive topic of debate. They don't even know the mineral, like the lattice orientation of the mineral, because to have iron be solid at that pressure and temperature, they can't compute it. And so there's some theories that say that it uses a helix structure, and there's some theories that say it actually uses a cubical structure, and that it slides around as it's in its cubical structure, and it's allowed to shift and move, but it's still solid. But yeah, it's a topic of debate. And if it were liquid, the whole thing doesn't work. So let's get into some geodynamo theories. I'm going to pause for a quick drink of water again. All right. So, from Sir Karl Popper, insofar as a scientific statement speaks about reality, it must be falsifiable. And insofar as it is not falsifiable, it does not speak about reality. We have the solid inner core, at least a few 100 million years old. It grows as the planet cools. we have the liquid outer core. Convective and Coriolis motion of conductive fluids creates helical currents. And sorry, just one moment. Convective and Coriolis motion of conductive fluids creates helical currents. So you have hot to cold, liquid iron, and nickel in the outer core, not the inner core, but the outer core. So the inner core is solid, the outer core is liquid. And the hot core is supposed to be the surface of the sun, and the mantle is way cooler. So you've got this convection going on of hot to cold and hot to cold of the outer core, and the Coriolis motion of that conduction or of those convective currents causes a helical pattern or a helical current, and from that you get you generate a magnetic field in their theory. And now that magnetic field that you generate helps to drive motion. So you're generating a magnetic field, and it's helping you to drive motion that perpetuates the process of continuing to drive the magnetic field. So you get a nice little, chicken and the egg thing going on, and that conveniently the chicken was just there to get you started. And as the Earth rotates, the Coriolis effect influences those convection currents, organizing them into the helical spiraling columns. And a turbulent movement of the molten metal generates electrical currents, causing the dynamo effect. Now, the rotational movement of those helical currents is said to be the cause of secular variation. What I mean by that is, all right, cool. So we got a picture. So these are what I'm talking about when I say the helical currents or the convection currents. This is what the motion of the liquid outer core is said to be doing. And as it's doing this, there's also a drift occurring of these columns that goes around the inner core. And that drift, as they go around the columns, around the inner core, thanks to the Coriolis effect, is what causes secular variation. So that's what they say causes all those anomalies we were getting into earlier. Now, let's really quick. We have to talk about a very important part of this whole thing. So before we can really even talk about the Reynolds value, I may have gotten a bit ahead of myself here. There is what's called the Curie point, and the Curie point is the point at which ferromagnetic minerals lose their magnetic properties. And those temperatures that we're getting into in this outer core are far, far hotter than the Curie point by by orders of magnitude. Now, because of the static buildup and because of the great speeds of the rotation, they assert that they are able to generate so much static charge that the Curie point is irrelevant. It's able to stay above what's essentially is the magnetic Reynolds number. So then the Reynolds value is the rate of advection, or the ratio of advection of magnetic field to the magnetic diffusion. The magnetic Reynolds number in geodynamo models plays a crucial role in understanding the magnetic field generation. It is defined as the ratio of magnetic advection to magnetic diffusion. In the context of the geodynamo convection, the magnetic Reynolds number is a key dimensionless parameter that influences the behavior of the magnetic field within the system. The magnetic Reynolds number value determines the supercriticality of the the RM value determines the supercriticality of the magnetic Reynolds number, with values above 1 indicating a supercritical regime. So that means that you're able to maintain your geodynamo. And that parameter is essential for assessing the efficiency of magnetic field generation processes within the Earth's core and is a fundamental aspect of geodynamo modeling. Understanding and analyzing the magnetic Reynolds number provides insights into the dynamics of the geodynamo system and its magnetic field generation mechanisms. So, the magnetic Reynolds value. So here is how that is calculated. You have RM is equivalent to, with the magnetic Reynolds number, is equivalent to the curl operator, which is represented there by Nostra, and that's multiplied by the velocity field and the magnetic field. You take that over eta, the magnetic diffusivity, multiplied by the Laplacian operator, which is Nostra, or the square of Nostra there, and then you've got U sub 0 is the velocity scale, and eta is the characteristic length scale of the velocity field. So the magnetic Reynolds number is crucial in determining the behavior of a self-sustained dynamo, and the Reynolds number has to stay above 1. That's what indicates the rate of buildup of the magnetic field is higher than the rate of decay. That right there is the crucial point of all of this, is that the rate of buildup of the magnetic field has to be, in their theory, it has to remain higher than the rate of decay. And if the Reynolds number is less than 1, that means that the dynamo is not going to be able to sustain itself. In the context of the Earth's magnetic field, the Reynolds number, it helps in understanding how the Earth has maintained a relatively steady magnetic field over its history. I think we all get it. So, the partial derivative of B in this equation, this would be the magnetic induction of the geodynamo, and it is the rate of the magnetic field with time. And then you've also got another derivative here. Nosfer times U times B is the interaction of the velocity field and the magnetic field. And that allows you to deduce, you add to that the rate of decay of the magnetic field due to the ohmic dissipation. Now let's get into the ohmic dissipation. I'm just going to read this here. Ohmic dissipation. Ohmic dissipation represents the ratio of the magnetic field buildup to the rate of decay due to dissipation. Ohmic dissipation plays a significant role in draining the mechanical energy stored in the magnetic field, converting it into heat. Interaction between the velocity field and the magnetic field leads to the buildup and breakdown of the magnetic field, with the dissipation balancing the energy loss. A critical condition arises when the system becomes unstable due to the exponential increase in the current and retarding torque, ultimately reaching equilibrium. This dynamic interplay between the magnetic Reynolds number and the ohmic dissipation is fundamental in the context of the geodynamo theory and magnetic field generation. Magnetic diffusivity. So, hopefully this is kind of making sense that we have a lot of problems in the core here, in that we have something that's way too hot and has way too much pressure, and then when we actually go digging down, it ends up being even hotter and having even more pressure than we anticipated. So, and they have a million. We'll get into that in a second. Let's really quick talk about. There was an attempt to do a physical geodynamo model, or like a physical dynamo that was kind of like the Earth's geodynamo, their theoretical geodynamo. That was done by Professor Dan Lathrop. It was a 3-meter steel sphere filled with molten sodium, and they spun it to mimic Earth rotation, and adjustments to the speeds and the textures were used to try and generate electrical currents within the sodium. And they were aiming to replicate Earth's magnetic field without external power, but they decommissioned it since it didn't meet any of their initial hopes. And it's currently being overhauled. Now, the thing was crazy. I can't remember the exact speed that it spun at, but like he wouldn't even let students in when he ran it at full speed. And even when they ran it at low speed, everyone had to clear the room. There's a picture of it. You've got these rings, and then you've got the inner sphere. So with geodynamo models, we have dynamic models. Dynamic models account for real forces and real masses. If dynamic models are properly conceptualized, then they should provide an equal or greater degree of accuracy to kinematic models as far as predictions go, but with less computational efficiency. Numerical simulations are said to be dynamic within their simulations, advances in computational power have enabled detailed numerical simulations of the geodynamo, and they aim to reproduce observed features of the Earth's magnetic field, such as field reversals and secular variation. They aim to reproduce it. They haven't been very successful so far, but they'll still give you lots of predictions. So kinematic models do not account for real forces and masses, and they use the Boissonnesque approximation rather than full Navier-Stokes approximations. Basically what that means is that they use density variations, or the density variations in a fluid are negligible except where they appear in buoyancy terms. and the calculations are just based on fluid motions, and those are used frequently for computational efficiency. So that's about it on geodynamo theories. We went into, now like I said, they're dynamic. They have dynamic models and they have kinematic models, but really, when they actually try to do predictions of where the magnetic field is going, it really is just pure, not numerical simulations. They're not really attached to reality. They're not looking at orientations. They're not looking at it's a game of computation and computation efficiency when you start looking into this. And as far as simulating the geodynamo goes, you should know that they have not simulated it. They can't. The Earth spins too fast, straight up. And I don't have a slide for that in here, but maybe I can pull it up once we go through the presentation and show. There's a quick video we can watch to talk about that. But essentially, it's many, many orders of magnitude. It spins many, many orders of magnitude too fast for them to do a proper simulation of even one magnetic event within the geodynamo. So let's talk about alternative geomagnetic theories. So the flat Earth vortex theory is the idea that we live in a magnetic toroidal field, and compasses in the magnetic field align toward the center of the vortex. And the Earth's circular toroidal field would be this here. And then you would see flat Earth is suspended in the center of the toroidal fields. We would live on a disk here. So this is the side of the flat Earth. This is what the flat Earth disk in space actually looks like, kind of. Here's a picture of what that might look like from the top. Looks kind of familiar. Here's a couple more pictures of what that might look like from the top. Now, this on the left would be actually a magnet. And interestingly here, if we look at work from Ken Wheeler, he's showing in this image that you have a magnetic, so the magnetic field in a magnet, it would be, so going back, sorry, let me clarify here. So going back to this image, you have the toroid. That's what these big circles here are, these big shapes. These would be the toroid. Now, this vortex here, this would be the hypertrochoid, the inside of that vortex. Now, what we have in this image is we're showing that the magnetic field, these circles that terminate on themselves, are expanding outwards into the sky if we had the dielectric plane in the middle here. And so here, what you notice with the dielectric field is that you actually have all these vectors pointing towards the center of the vortex, or the center of the North Pole. So if you're wondering what's causing your compass and your dip needle to orient towards the center of a vortex, it might be the dielectric field. Here's a picture of a magnet in a ferrocell. And what that is just a device, or it's just a method that allows you to use a certain type of oils within glass to see the magnetic field. Here's another picture of a magnet under a ferrocell. Now, interestingly, if you look at the side of it, you can see this would be a block domain wall, or the side of the magnet. You see the center of the vortex on each side of the magnet. And interestingly, it looks kind of like the way that an electric field circuit looks from Charles Proteus-Steinmetz's Impulses, Waves, and his book about magnetism and electrical fields, essentially. And here's another picture showing from the side. You have the block domain wall going through the middle, and then you would have the North Pole here, and your South Pole would be on the other side here. And really quick, just going to play a quick video. I'm going to pull that up. I'm going to have to share with Discord. Give me 1 second. right. You guys see? I'll give you guys a second. This is showing the path of the planets as projected over a toroidal vortex. You can see they interestingly all kind of tend to match that flower of life geometry. All right, now I'm going to have you move back over to guys a second to tune back in. So here's just another picture showing a top-down. Now this is a Neo-Tychonian model. This is showing essentially the Earth in the center in a geocentric solar system, or not a solar system, but a geocentric universe, quote unquote. But the extrapolated over a flat plane with the way that a celestial sphere works, it would look very similar in its geometry to what we see here. Here's some more images showing the ferrocell and how that geometry looks quite similar, specifically in this image, to the path that the ISS takes. And then you have the motions of the celestial bodies. Now, here's another image showing kind of what it would look like, right? You have the flat Earth here. You have the plane that we exist on, the inertial plane that we exist on. And then you have the toroidal vortex that we exist within. Now, here's just one other possibility. Let's say we throw, actually, this is just one possibility for how this is all explained, right? Is that we could literally have a barn magnet underneath the Earth, and that what we witness is just the top of the North Pole. What exactly is causing it, I think, is more likely to be electromagnetic, but I couldn't say for sure. And shout out for Stone for this illustration showing just one possible way that we could have our magnetic field just existing underneath us in the ground. So thank you. That's everything. And thanks for being here.
Dude, you killed it. It was a great presentation.
Yo, thank you.
Covered every aspect of it. Great.
I didn't want to talk about it without talking about like why they have to say some of the things that they say. Oh, I wanted to play that video. Yeah, let me pull that up really quick. Of the guy talking about them trying to model. It's just a minute and a half long. Ooh, how am I going to play it?
Ooh, we're going to have to get the assistant out.
Yeah, I'll pull the assistant
Actually,
out.
Andrew, can you restream it for us, bro? Or anyone who's available?
Wow, I can't spell Twitter.
Dude,
But yeah, thanks everyone for tuning in. Bear with me for just a second while I pull this video up. What were we saying, Alan?
So I said Shane would be clowning us so hard right now, dog.
Oh.
We can't play the video on our own.
Yeah, I'll pull the assistant out. Let me boot up the virtual machine. Mm-hmm. So yeah, I'm just pulling up the video. It's a lot of waiting for a 1.5 minute long video, but oh well. Oh, there he is, Mr. Miller. Or is it Mr. Morley? What's up, Morley? All right.
Major caveat.
Oh, Morley, is that you?
Hey,
There
Morley.
we go. Yeah, it is.
All right.
One major caveat is that we cannot simulate the conditions of the Earth's core exactly. And that's because it rotates so fast. And, I'm not sure there's a better way to depict this other than these non-dimensional numbers, so I'm going to stick with these for now. So on the y-axis here is the Rayleigh number, which is related to the amount of convection going on. And the x-axis here is related to the Ekman number, which is related to the inverse of the rotation rate. So faster rotation is to the left, more convection is up. The Earth lives in this blue box up here. Most of my simulations are down in near this green box. I'm pushing a little bit to the upper left as we can, but it's a little bit hopeless. One of my colleagues in the UK computed to get down to Ekman number 10 to the minus 9, so here, not even Earth conditions, using 54,000 cores in parallel to compute one magnetic diffusion time, which is not very long. You would need 35.6 years of straight, constant computation time, which is a horrible PhD project. So this is not happening. I mean, sure, 54,000 is maybe a little bit outdated. Now we can do millions, but it's an order of it's an order of magnitude effectively problem. So we have to rely on this dash-dotted scaling law trajectory. We have to see if we understand the physics well enough in this part of parameter space to scale up to the Earth. That's the hope. That's the mathematical part of what we do.
Well, here's the hoping, brother.
Thanks, Morley, for sharing.
Dude, my man said, yeah, it would be a fruitless endeavor to get your PhD thesis on this, dog. Like, so go ahead and do a different one.
Yeah. So there you go. I would say that the magnetic field is probably one of the strongest evidences against the globe theory. It's probably one of the greatest evidences that we have no idea what's going on. Because it seems to kind of be the origin of a lot of it. A lot of what defines existence seems to be very reliant upon it.
So what it appears to happen, or what appears to be going on here, is that they had a preconceived notion that they live on a ball, and they got this magnetic field they have to explain, and using an unlimited amount of kinematic theory and computational power and violations to the kinematic principles of assuming causal forces to even do anything, they don't have a way to explain the phenomenon for which they can measure and everything, but that they can't fit it into the spherical rotating model because it would be rotating too fast, it would be too hot, there would be too much pressure, the magnetic field would never be able to realign with the Curie point. So it's all just very, it's like it's fan fiction at that point, right? It's not even It's not even an actual theory. It's just for funsies. It's like, here's what a bunch of people think for fun. Like, not even an actual explanation to anything that they could ever put in anything tangible, right? There's a guy trying to do it, and he's saying that it's a fruitless endeavor. He's like, go ahead and don't even try it, lads.
Too much computational power required.
All right. Well, that's about par for the course, honestly, when you start looking into the things that are supposed to be mutually exclusive. And one of the things that you showed earlier, that the axial alignment was pretty funny, right? The magnetic field isn't even axially aligned with the supposed causal mechanism of the field itself. It's like, sweet, dude, that's cool. That definitely checks out. That's something I want to believe in. Where do I sign up for that? Like, when you go to a seminar and there's like pyramid schemes and you're like, you're obviously not falling for it, but they're like going through the rigmarole. It's like, imagine someone sat down for a heliocentric seminar and they were just like, okay, so here's what we can't do. And they just explained it in that way. And you were like, you had to buy into it. You know what I mean? You had to go, you know what? I think this is what I want to go. This is how I want to go with
Well, that's
for my
why
interpretation of the world.
like I really wanted to mention that when I picked up an intro to seismology book like a year ago, I was blown away because like the whole first unit was just all about astronomy. It was like, oh, we have to make a bunch of assertions about the solar system first before we can start, that way we can just assume it's a ball when we start doing seismology.
And I also like the Newton shell theorem thing. That's hilarious.
Oh
The
yeah.
inside of the ball. The inside of the ball doesn't work, but hypothetically on the outside, like, you're good to go.
Yeah. Yep.
But good luck explaining what's happening on the inside in any sort of meaningful way. They're just like, no, it's just downward vector uniform all the way in, boys. It's like, have you met my friend Newton or whatever? The one you guys all deify?
Yep.
Yeah, dude, that's fascinating, dude. What an awesome presentation. Does anyone from the panel have any questions? Or anyone in the chat or anything?
Well, cool. We can go ahead and close out the stream then. Thanks, everyone.
All right.
Hey, I don't have any questions, but you gave me an idea that for another great presentation you might want to think of doing all the different unfalsifiable claims for the globe, because there's multiple. So you mentioned one just earlier where you said, oh yeah, it's unfalsifiable. It just made me think of like how many actual unfalsifiable claims do they have?
So many, man.
And I thought,
All
I
of
thought
them.
that might be a good presentation.
Yeah. No, absolutely. Good thinking, bro.
All of
I'm adding that to
geology,
the-
all of seismology, all of geodynamo theory, all of it's all assumptions. All of astronomy. It's insane. Most of it riddled with paradoxes.
We'll have to do the inverse so it's a shorter list. What they can
What they actually
falsify.
can prove. So basically everything that we can use to actually build a real theory.
Yes.
Maybe you could turn it into a series called Unfalsifiable Claims.
Ooh, I like where your head's at.
Yeah. That's good. Flat Earth science. Testable, objective, honest.
Oh, where's the flat Earth science image at, dog? Need a graphic for that. I saw you make one earlier.
It's on Twitter.
Will I be able to pull it up in time? No. Nope, I'm abandoning it. All right, so I think we're going to wrap up now. Toby, you want to close us out, brother?
Yeah, so thanks for being here for geomagnetism. I anticipate there will be a part 2 because there is a lot of information on this topic. On Thursday, come around here to Aether Cosmology for reading night. I'm not totally sure what we will be reading this week, but I'm sure it will be fun. Woohoo. So tune in for that here on Aether Cosmology over on Space Audits, and possibly ADL will be streaming. And then also tune in on Friday for Flat Earth Fridays with the Level Heads, hosted by Proud and Sacred. And then on Monday, we will probably do another Twitter space, so tune in for that. But we'll probably stream that as well. And then next Tuesday, always at 7 p.m. Eastern, Aether Round Table number 30. We'll be hitting 30 Aether Round Tables, so that's pretty cool. So yeah, thanks everyone for being here. Thanks for tuning in. Thanks for listening. Also, Aether Cosmology on YouTube, just 1,000 subscribers. So thanks everyone for the support. Much appreciated. Hopefully we can keep doing what we do. Who would have thought that people would want to tune in to listen to Flat Earth Science and to listen to Flat Earthers read PDFs? But apparently some of us want to listen to that. So thanks again. Take care, everybody, and have a wonderful